let's take a look at one of these examples with a spring. So we're going to do a 0.5 kilogram mass is placed on a vertical ideal spring. The spring is observed to stretch 21 centimeters before reaching equilibrium. What is the spring constant of the spring, and how far will a 1 kilogram mass stretch the spring? All right, so let's look at the information they gave us. They told us that when I hang this 0.5 kilogram mass, so this is 0.5 kilograms, it stretches it 21 centimeters, so 0.21 meters. And it wants to know what is the spring constant. Now, when I hang that new mass on there, it's going to hang at a point where we have equilibrium, meaning it's just hanging there, it's not accelerating. So that word equilibrium is telling me that the sum of the forces is going to be 0 in this scenario. So I look and I see I have the FEL pointing up minus mg pointing down. And FEL is kx. And notice I'm not using the vector direction on this one. It's not a negative kx here because I've already indicated that its direction is positive. I'm not trying to use the displacement to figure out the direction of the force. I'm labeling the direction of the force. Okay, so to find the spring constant, k, so k is going to be mg divided by x. And so if I plug in my numbers, I have 0.5 times 9.8, all divided by 0.21. And so I solve for my spring constant, I find out it's 23.3 newtons per meter. So it requires 23.3 newtons to stretch it 1 meter. Now that doesn't mean the spring can actually stretch 1 meter, it's just how much force would be required to stretch it that 1 meter. Remember, Hooke's law is assuming ideal springs, meaning that they are going to be following a linear relationship between force and distance. And most springs that follow Hooke's law have a certain range that this works for. Right? Now, the second part says, well, what if I hang a mass that's twice as large on it? Okay, so I still have the same spring, so the spring constant's the same, but now I have twice the mass. So a little thing we can do here is, because the spring constant is the same, I can take this and I can go, all right, well, if I do k times x equals m times g, if I go ahead and double the mass, what am I going to have to do to the x if k and g are constants? Well, I'm going to have to double the x value. And so instead of stretching 0.21, it's going to stretch 0.42. I could also go ahead and plug in my 23.3, plug in my mass of 1, my 9.8, and solve for x, and I will get that 0.42 meters as well. But this is more of a relationship that it's a 1-to-1 ratio in there.